Okay. Okay, so there is it's not how do we link your antennas, and then I'm interested in manufacturing. That's why I was very much interested in this 3D printing technology. So this is very basics. I didn't know much because the audience here into antenna theory. So to generate so very quickly, just because I know that all of you have done bachelor at least and the master courses. You know that in general, if you want to get a high directional antenna for space application, as an example, you need an electrically large antenna. Okay, so but if you want an electrically large antenna, you know that we go through a Fourier transform, which is possible formally, and of course, having an electrically large antenna is not enough. If you want a lot of directivity, 30, 40 dB, sometimes for some application they need 45, 48. Okay, so it's a huge number. It's not just about electrically large, but it's about illumination. Okay, that is the key point. There is a strong impact when we talk about Leaky-Wave antennas, and I try to be more clear in the next slide. So we want antennas that are electrically large, but we want uniform illumination. Okay, approximately uniform illumination. So we talk about traveling wave antennas in general. And the Leaky-Wave antennas are just a possible type of traveling wave antenna. These are possible implementation. It can be, we call this type of antenna 1D, because the propagation is going from right to left or from left to right. Or we call this one 2-dimensional Leaky-Wave antennas, because in this case the feeding point, which is generally just one, is in the center. And then the propagation in this case can be radially propagating. So here is 1D, here is 2D. It's just how you see the propagation curve, okay? So, why we like traveling wave antennas? Get opposite figures with respect to a resonant antenna, okay? Because, okay, so impedance bandwidth for sure. Then you can have also a pattern that can be larger or not larger. Okay, if there's a big beam with bandwidth, then you wanna point in the same direction over a larger bandwidth. Okay? The point is that in this specific case, there is in traveling wave antennas, you can integrate the feeder within the antenna. Okay, so that's the point. Because as an alternative, as also Jose was showing, you need to design an array. But with array, you need more feeding points, okay? Which we have generally here, just one feeder. And this feeder can be, if it is well designed, fully integrated within the structure. So these are the possibilities. So 1D and 2D, we already discussed the difference. So Leaky-Wave antenna, so that's the idea. It's well known. It's a theory that was developed years ago, last century. And so what we have is a wave that is traveling, so that's why it's a traveling wave antenna, and in the meantime is radiating energy in free space. Okay, larger is the antenna, of course, bigger will be the directivity. Okay, but we will deal with something that you will know probably is dispersion. Okay, since there is a guided wave, if there is a guided wave, there is a waveguide, you will have dispersion. Dispersion means that the radiation of the antenna will change with the frequency. And as I was showing something before, because he was showing an antenna with 2 channels, and in this picture, I had seen 2 beams that were pointing in a slightly different direction. This is called dispersion. So dispersion is not just for materials. Okay, it's not just for materials. Dispersion for materials means that 2 different frequencies will have 2 different permittivity. Here we have that 2 different frequencies will get 2 different beams for the antenna, because there is dispersion in the waveguide. Modal dispersion, as you have seen here bachelor or master courses. So we are designing an antenna, but we are studying the propagation of a mode. That's why we call leaky mode, okay? So if there is a dispersion, you will have a wave constant for the mode that you are considering. This wave constant, beta, the real part of the wave constant, will control the pointing direction. Okay, so if you are propagating in this way, and then you are at a certain frequency where you have a certain phase constant, which is the real part of the propagation constant, you will point in this direction. Otherwise, you will point in this direction, or in this direction. Typically, the direction that is orthogonal to the propagation of the wave, to the direction of propagation of the wave, is the broadside. Okay, sometimes the broadside, but we are there. Okay. So there are two possibilities, at least most important, to generate to design a Leaky-Wave antenna. One is a Fabry-Perot cavity that you already know. Okay, Fabry-Perot cavity is like a cavity where you have a ground plane. You have, as you can see here, dielectric, possibly air, but then it's more complicated. Then you have a top plate, which sometimes we call it partially reflective screen, PRS. Okay, so this is the case when you work at a wavelength that is large enough to not see these slots. Okay, that is a frequency selective surface, partially reflective surface. I mean, when you go ahead with your career, step by step, you will discover that people like to call same thing with different names. Okay? That's the idea.
That's right.
Yeah? So that is also to add novelty to. So PRS, FSS. I mean, it's just a periodic structure, and the periodic structure can be homogenizable or not, uniform or periodic. I mean, if this periodicity, this slot is small with respect to the wavelength that we are working on, you don't see this periodicity. But still, if you don't see this periodicity, if the slot is very small, that doesn't mean that the field does not interact with the modalization, okay? That's the point. So it's a partially reflective surface or sometimes screen. In this case, the periodicity is not anymore so important. Still, you can apply like the Leontovich boundary condition that probably you know. And in the end, the radiation can go out. If the radiation can go out and this cavity is electrically large, you can get an antenna. It's like the Fabry-Perot interferometer. So what's happening? You can do an interpretation like continuous reflection. Then you get every time a ray that is going out from the cavity. And all these rays are in phase to radiate a directional beam in this direction. Okay, that's it. But there is a problem here. To implement this concept, which is amazing, you need a cavity that's rather thick. Lambda over 2, and okay, it can be a little bit thicker than actually needed. So that's the one of the limit. And then there is another point that the cavity is not easily filled by air. There is a dielectric, and people doesn't like the electric. I know some people, Pablo likes that. If you talk with Oscar, which is a Spain guy that you know very well, he doesn't like it. KTH, okay? It depends. But fortunately, these are just viewpoints. So just build up freely your viewpoint, okay? Because any application needs a different viewpoint. This is manufactured PRS. We did something. This is just a square array of patches. It's nice because in the literature you can find the closest form expression to manage this PRS. So you can define susceptance or whatever, an impedance in a most general way in a closed form, which is able to well describe the behavior of this PRS. Okay. And then you can use it to do transverse equivalent network to get the leaky mode I was working before. We did something in collaboration mainly with the Aalborg University, and just an example here, we were designing a feeder, which is a parcel feeder, which was working in a frequency range that was quite large. This is quite conventional PCB. It's not dedicated here, okay? So what you get is dielectric laminates, Rogers. You do laser etching, Then you use a foam layer here, and then in the end, what we have got that this dielectric layer and the foam, they are not thick enough to be seen as distinguished by the radiation, so you will get in average a permittivity that is smaller than 2. Okay, so that is a possibility. It's a very, very simple approach. What we get is a conical beam seen on a plane, as was shown before, or you can also, this is the idea, this is another perspective. You can also, this is the antenna that was fabricated. You can, which look like some perfect. You see, that's the section. This is an electrically large antenna, of course. And then we discussed that there is a problem. The illumination here is not uniform, because the leaky mode will not generate a uniform illumination, but at least it's electrically large. So you have a good directivity. The point is that you can also use more feeder. So you can feed a fabric cavity antenna with an array of feeder. Okay? That means that you are merging a little bit Leaky-Wave theory with array theory. So in the end, you will get the beam that was shown here. A beam that was that is now confined along the azimuth. Okay, here is a conical beam. So making this measurement is not easy. These are done with low-cost equipment, probably lower cost than yours. But they were done 10 years ago, so probably we can do better now. And so there is a little bit of instability because also these laminates, they bend a little bit, as was shown. No? They bend, they will change the electrical behavior. In the end, this is a conical beam, which means that you are radiating the same energy along a cone. Here, you are get a sector conical beam because you are using array theory. But there is a directivity, an high directivity. In the order here, it's not sure. This is the beam pattern was in the order of 15, 14. Okay, because of course, if you spread your energy along a conical beam, it's not the same if you spread your energy along a pencil beam. The directivity here will be slower, will be necessarily smaller. So this is a possibility, fabric cavity antenna. Okay, so this is another possibility. You see, we did a feeder that was completely different with port 1, 2, 3, not coaxial cable in these cases, but a slot with a sieve arrangement, a substrate integrated waveguide. That's the one play of us. And here the idea was to show that we can get highly isolated port, because there is another application that was not mentioned so far is full duplex antenna. Right? There is a huge interest in receiving and transmitting with the same frequency. You probably know, right? So you get one frequency and use the same frequency to receive and transmit. Okay, so imagine this antenna, you receive and transmit with, you transmit with port 3 and 4, and in the meantime, you transmit with port 3 and 4, you are receiving at the same frequency with port 1 and 2. Okay? That means that in the meantime, you transmit with port 3 and 4, you should not get energy in port 1 and 2. So you need highly isolated antennas. Isolation in the order of minus 60 dB, minus 50, minus 60. So this we showed the possibility of doing this with a Leaky-Wave antenna. Okay. Since here we are not having vertical electric dipole, but we are having slots in the ground plane. We are able to radiate at broadside, because when you put a PRS here, the PRS is not able to break the electromagnetic and geometric symmetry. So if you are exciting the cavity with a vertical electric dipole, you are not radiating at broadside. You are getting a transverse magnetic mode, an theta field that by symmetry should go to 0 exactly at broadside. Here we can go different from 0 at broadside. Okay, so but it's more difficult to do this, even though you get a completely integrated feeder thanks to the substrate integrated waveguide. Okay, and this was highly isolated. I'm not showing the isolation, but it's in this letter, which is actually very the same. Okay. So with the same PRS, you can do different design. Periodic Leaky-Wave antennas, another word. Periodic means that you can have still an arrangement of metallic patches, but in that case, the periodicity is comparable with the wavelength. Okay. So you know probably a rectangular waveguide. This is an exercise that we do in bachelor courses. It's a rectangular waveguide that is loaded by irises. This was an exercise that was done during the Second World War, essentially to design filters. You know that there was a huge advancement during the Second World War. Unfortunately for humanity, huge technological advancements are made during wars. And the idea is that there was to develop radars. Radar have to manage a huge amount of power, so you cannot use a lens made by the electric. Okay, so we need to still today, we need when we need to manage high power, we use waveguides. Okay, so this one is a periodic structure. You load the fundamental mode of this guide that can be TE10, as you well know, or 01, depending on the orientation. And using this loading here, you can look. This is the propagation constant multiplied by the period, because this is a convention also in physics. And you get, if you follow the frequencies on the vertical axis, so if you see here, you have a spectral region where you do not propagate, a spectral region where you propagate, you do not, you propagate, you do not, and you go on. You generated a filter. This is a simple exercise. And this one is called, so this one are stop band. Okay, this one is a closed stop band where beta dot phi dot the period is pi is a closed stop band. This one is an open stop band. Okay, don't get confusion. They are the same thing. The difference is that here you do not propagate it when beta is equal to 0. Here you do not propagate it when beta is equal to pi. Okay, beta dot p. So stop band, closed band. But you know that array theory will tell you that if you want to radiate at the broadside, you need to have everything in phase, right? So everything in phase means beta equal to 0, because this is a phase. Beta here is the real part of the propagation constant. So it's giving you the phase distribution inside the guide. So if ideally you open this web guide, you open it, and you ideally give to the radiation the possibility of going out. If you open this web guide where beta is equal to 0, ideally you can radiate at broadside. Okay, but there is a problem. So this is just a possibility. Okay, periodic load within a waveguide. Another possibility will be used as an example, a load that has a glide distribution with bad symmetry. And in this case, I'm also adding the phase constant here. The phase constant and the attenuation constant is in the giant color. See, where you have a open stop band, you have a big attenuation. That is the reactive behavior of a classical guided mode. You are here under cutoff in this region because you introduced the stop band, below cutoff because you introduced the stop band because you were periodically loading this waveguide. Okay. That's the idea. So the idea is, okay, but if we open this waveguide, can we radiate at the broadside? This is a problem that is generally well known, because before doing all metal things, all metal periodicity with the slot on top, there is a huge literature with this structure. This is a grounded electric slab. Huge literature because you can do this with PCB. So in the 90s, with patch antenna and whatever, people started to study this kind of periodic structure. So even before all metallic, they studied this one, even though the first type of Leaky-Wave antenna was slotted waveguide. So it's a repetition. Life is a repetition. We started with the rectangular waveguide, we open waveguide, we get PCB, then we get periodicity with PCB, then we discovered that, okay, let's go back to slotted waveguide antenna, because now we can do better at millimeter wave frequency as an example. No? So it's a philosophical approach, but it can work. In any case, there is a periodicity here, you know, and here there is a surface wave. You well know that you can guide a wave even though the structure is open, because this is an open waveguide. Okay, you can find this in common books like Collin or the most important book. There is a waveguide. Okay, so a waveguide that is guided here is a slow wave. Okay, if you introduce this periodicity, you will transform the slow wave in a fast wave. A fast wave is a leaky mode, because a leaky mode by definition is a fast wave. You will get radiation, okay? But here the periodicity will be such that you are comparable with the wavelength we are considering, okay? So you get essentially space harmonic, because you know that like a time domain signal can be decomposed, a periodic time domain signal can be decomposed in Fourier harmonics. electric field inside the periodic waveguide can be decomposed in space harmonic. It's just the same mathematics. A little bit more complicated here because the electric field is a vector. Okay, that's always the same story. We need to use vectors. So in the end, you have space harmonic. This one is you get that each space harmonic will have a propagation constant. Okay, they will have different phase constant, but all of them will have the same attenuation constant. The attenuation constant can take the account of losses if you have losses in your materials, or can take into account of the fact that the radiation can leak out. That's why we call Leaky-Wave antennas. Okay, leaking out. So we can do also this kind of periodicity, which are radial periodicity. Okay, this is an antenna that is a 2D Leaky-Wave antenna with a radial periodicity. Any cut you select here, you will see the same behavior of this linear structure. So the Leaky mode that will be propagated here will be the same in this radial periodicity, just to give you an idea. But here, see, we have that the periodicity is comparable with the protein. So what do we do? And in my university in Rome, they did it since 30 years ago. So they are very expert. We do an analysis, a modal analysis of this structure. It means that we look for the phase and attenuation constant in this periodic structure. And to do it, you need numerical computing, numerical code, and most of the time we use Melville moments in-house. Okay, it means that when in your bachelor or master courses, you have seen that you can get the propagation constant of the T10 mode of the rectangular waveguide. We get here the mode that are propagating in this periodic structure. The nice thing is that since this structure is periodic, you can just study the unit cell, just one cell, because then you can apply what we call periodic boundary condition. So you just study one unit cell because you know that looking right or looking left, you will get the same behavior. So it's numerically efficient if you are able to code properly your code. Okay. In any case, what we get is a dispersion diagram because there is modal dispersion. Okay. So if there is modal dispersion, you will have beta and alpha, or generally k, that is dependent on the frequency. And that will make your antenna frequency dispersive. So what we get is beta normalized with respect to K0. This is a fancy thing that we do. And then alpha, so real part and imaginary part. Typically, when you work in a closed waveguide, you know that, and in absence of loss, so lossless, you get that the beta is different from 0 when you are above cutoff, and alpha is different from 0 when you are below cutoff. Here it's a different word, okay, because essentially you are in a periodic structure. So you have that you can have a backward, a forward space harmonic. So it means that the beta can be negative, but also can be positive. So this is beta, that's the region. Okay, this is beta. Look at this axis. Can be negative and positive because there is a decomposition in space harmonic. Okay, and this one is alpha. Okay, the attenuation constant that is always different from 0, except for one point, because you are leaking out energy outside. Okay, you are leaking out energy, but here you have an open stop band. Okay, so the behavior that you were seeing before in the rectangular waveguide loaded with irises here is just for one frequency. So it means that beta equal to 0, where beta is equal to 0, you cannot leak power. It's incredible. You want to radiate at the broadside because essentially when you radiate at the broadside, it means that you are illuminating this slot here with the same phase. So Leaky-Wave theory is just a tool. There are a lot of people in the world that they can design this antenna using Leaky-Wave, using array theory. Okay? Because you are illuminating slots here. Okay? So that's the point. So where you want to radiate at the broadside here, you will get that alpha is equal to 0. Alpha is equal to 0 means that you cannot leak power outside. So the different solutions were proposed, and then you change the strip arrangement. You make two strips, one different from the other, and here you get that alpha is equal to different from 0. Because you are introducing an asymmetry. Okay? So this is just to give you a big picture. I understand that it's not easy to follow. Then I go to the manufacturing side. If you have not a good experience in this idea. But that's it. In the end, what you get is beta and alpha. This is the I'm getting here the modulus of alpha. That's why you see that it's positive. Okay, but that's the idea. Then alpha, so the modulus of beta, and then this alpha that is never different from 0. So this antenna, with respect to this one, can radiate at the broadside. Okay. So you are making an antenna that is planar, with a feeder that is fully integrated, that is ready to the broadside. Okay? Doing the same with an array theory, with an array, it means that you have to use multiple feeders. Okay? It's a bit different, probably a little bit more complicated. Or then you can do different shape, sectored, and then you can get this beam that are highly directional. Still, we have the same dispersion, the same behavior, but you can get this beam that are fancy, because you can get a fancy beam scanning super side. So you can do different things with a planar antenna. PCB, much more thinner than a fabricated cavity antenna. Okay, here the thickness of this PCB is much smaller than λ/2. So thick, and it's not thick and planar and well integrated. Then you can use lenses here to try to adjust a little bit the illumination. So you can use different configuration. This was done also in collaboration with Pablo Padilla, that is in Roma 3, and always with Aalborg Simon Podilchak, that probably you have seen around. This is what happens in a simulation. That's I want to show you. This is the feeder. This is the same grounded electric lab. You can see a section. There is one source is injecting here the energy. Look, the energy is going right and left, but since I am close to beta equal to 0, it is a standing wave. There is not propagation. But since there is a leaky mode, look at this. Look at the amplitude here. It's modulated. Because there is an exponential decay. Okay? So even though I have got an antenna that is planar with a well-integrated source, I can use SIWV, as you well know, I can use different approaches. I am getting the farthest possible illumination with respect to the uniform one. Okay, as a matter of fact, here I'm not getting a well-defined plane wave, because if you get a plane wave, it means that you get a uniform illumination, you do the Fourier transform, and you get a very directional beam. Here, the Leaky-Wave is attenuated with an exponential factor, so it means that my uniform behavior is really far away from me, okay? But you can do something, because you can try to modulate. You can try to modulate the strip, the periodicity, to adjust this, okay? It's not simple, but it's something that you should work on. So this is just a screenshot. We already talked about it. Now, the point is that these antennas are made by the electric. And this is just to show you, okay, here, this is an antenna. This is the same antenna that you see before. This is the gain, the peak gain, as a function of frequency. Of course, when you have the peak gain when you have a pencil beam, then when you move the frequency, you get typically a conical beam, so the directivity goes down. But what you have to compare here is the red and the green curve. Okay, red is lossless, green is lossy dielectric. We are here at 20 gigahertz. If you go 40, 60, or 90, it will be even worse. So a lot of people, if they see 1.5 dB that are lost due to the electric losses, they are really unhappy. Okay. For space application, 1 dB, you can sell your mother to get 1 dB. That's what they say. No? That's what they say. It's not it's a citation. So, what's the point? What we did, okay, what's the possibility to design a Leaky-Wave antenna without the electrics? Okay. We started to do all metal Leaky-Wave antenna. Okay, one possibility is this one, locking this one. Okay. But here there is a problem that alpha is so big, because you are starting from a structure where you have alpha that is big due to the fact that there is a reactive behavior there. When you open, slotting this structure, we are still not able to control alpha as we would like. Big alpha means that the exponential tapering of the Leaky-Wave antenna is very fast. When you have an exponential, if you have a big alpha, it means a big multiplication factor at the exponential, you get a very fast decay. If you get a very fast decay, the antenna will never be electrical enough. So there is always this connection. So this one, we are studying it with Guido, Sorbonne University, and we are still having some problem, because it's not easy to control this alpha, because you start from a configuration where alpha is already big, because there was a stop band due to the fact that you were generating a periodic perturbation. Another possibility is to, instead of using a dielectric, and we are working on it, and we have a draft on Aki, just because this is probably a good idea, hopefully, is to, instead of using a dielectric, use a periodic structure on the bottom. So you make your waves low, because you know that when you get the propagation within a waveguide, if you go back to a rectangular waveguide, a parallel waveguide, you will find that without do nothing, you get a fast wave. There is a fast wave there. Instead, we make slower the wave by introducing this obstacle, and we get that here we have a slow wave. Then we put another plate on top, and we introduce slots. These slots here can support a leaky mode. So we are getting, the idea is to get the same behavior than before in the absence of dielectric, because that's much better for high frequency. So we are studying this and we want to manufacture this, okay? You can do a 1D Leaky-Wave antenna, but you can do also a 2D Leaky-Wave antenna. This is what we call Brillouin diagram of this structure here. Because then what you can see here, this is the K0, is the line of light, we call it. Then if you are above this line, you have a fast wave. If you are below, you have a slow wave. So in this region, this is the dispersion curve of the mode supported by this structure. You have a slow wave. Okay. By adding slot, you will perturb the propagation of that slow wave, and you will get a leaky mode that will be here in this region. That will be able to radiate. Okay. In the absence of dielectrics, that's the idea. But this is not the only possibility. There is also another one. The possibility is to use just corrugated structure. These are well known in the literature. Because then, you know that in general, you can support a surface wave with enough space made by a metallic. These are TM surface waves, so transverse magnetic waves. You introduce a perturbation, and with the perturbation, you can generate a leaky wave, one antenna, 1D or 2D. So this is another possibility to get a fully metallic antenna. You will define a unit cell, and solving this unit cell, you can get the dispersion. Okay, this is the dispersion typically that you get. If you don't do nothing, since there is a periodic structure, you get an overstop band. So you get a point where beta is equal to 0 and alpha is equal to 0. Okay. So we are working with a PhD student to suppress the overstop band, and we did it. Okay. Here you have alpha is the red curve is the attenuation constant of the structure where we introduced an asymmetry. So you get that alpha never goes to 0. This other blue, the blue curve here dotted, alpha goes to 0. In this case, it never goes to 0. So we suppress the overstop band, but we want to increase the performance. When I say increase the performance, I want to get the antenna that has the highest directivity, so uniform illumination. And I want to get also, possibly, if you are radiating at the broadside, the maximum gain and the maximum bandwidth, okay, which is something challenging, because getting high gain and high bandwidth means the largest possible bandwidth where you radiate at the broadside with the highest directivity. So, and we do this by working on Leaky-Wave theory, okay, because it's demonstrated that you will radiate at the broadside at the frequency where beta is equal to minus alpha. Beta is smaller than alpha. Okay, so there is you can use Leaky-Wave theory to design this antenna, but yet you can use also array theory. So that's it. I think it's 1 o'clock. This just to give you an idea. In the end, what we are optimizing this antenna here with the suppressed overstop band. We are working on this one, and we are discussing how we can manufacture these antennas that are all metal because they are minimized losses. Keeping in mind that we can do a 1D design, so we can get an antenna, a wave that is propagating from left to right and from right to left, or we can do a 2D antenna by using a radial periodicity. And in that case, you will have a feeder in the center. Okay, that's it. Thank you.
Thank you so much, Davide, for the presentation. And now we have some minutes for questions. So
I have questions.
Yeah.
I suppose that is the reason because you are looking for a 3D printer to manufacture this kind of structure.
Yes, to involve also students because they are happy to do this kind of theoretic studies, but never go to the hardware. For them, it's a little bit frustrating sometimes. some of them they wanna touch hardware.
Yeah.
And also for publishing software. I mean, you can there are companies that can manufacture for you.
Mhm.
Then the point is, I was very interested by your presentation because my fear is always the surface roughness. But if you go up in frequency, but probably manufacturing with coating, it's an option.
I think that we can talk about this because or Pablo or myself, we can manufacture some samples of this, doing the chemical coating. That is the first for the best for roughness, as you say, and perhaps we can collaborate doing the rest of these things.
Yeah, and also take in mind that our perspective is that in 3-4 years, this is going to improve even more. The 3D printers in terms of metal, for instance, years ago, we were thinking never, this will be never the option. And now we see that they could be the option. And in terms of...
And here the thing is that it's not totally closed, so you can do perfectly the coating, so it's not so difficult as if it's totally closed.
We can even demonstrate technology because the point is that the tolerances that may be requested here for this prototype can be different from yours. Maybe worse, maybe better. We don't know because then any type of antenna can suffer the constraint of the technology in a different way. So you can design something at 20, then you go 50, then you go 90. Then
I mean, today the lithography printers, they are very precise.
So that's interesting.
And well, can be done something in 20 or 30 and go up. And just said that I mean that the concept that you are proposing here is almost valid from in 20 and 30.
That's the point. You can just scale this antenna. Once you got to the dispersion, you upscale, downscale, and you get the same. Then also when you do this metallic printing considering just all metal, I know that people they use sandblasting because sometimes they get in any case a surface roughness, so they use sandblasting to try to.
Also sandblasting for CNC. They also use
Questa è sabbiatrice in italiano. The sandblasting.
Aquí es que es pulido de arena, es que es pulido. Chorro de arena.
Because arena is also a way to say sabbia. Sorry, by the way, my presence here has made this meeting in English. So
don't worry.
I'll make this meeting in English. Next time I'll try.
You can consider a new interpretation of English.
I mean, and in general, a bad English spoken by Italian Spain people. Anyway, I need to improve my. I should study Spanish because it's not so difficult. For me, it's not so difficult. Just when you speak very, very quickly. Now, the last point I was telling you that once we did some prototype without tapering, it means keeping this exponential tapering here. Then we are working a lot on tapering. Right in these weeks, I'm working with José Torre. There is Miguel that is working with me.
Miguel Poveda?
Yeah, Miguel Poveda. And we are not working on your metal side because we started from the metal segregating here. Because really, we believe that there is room to show. José is working on tapering since 20 years. So, but doing this at broadside, it seems it was never demonstrated. So we want to understand how much we can make uniform this illumination. It's an asymptotic goal. You will never get a uniform illumination, but you can improve a lot. Then we will do the same with the diesel metal design. So there is a lot of room for many prototypes.
And also, how much bandwidth are you going to maintain the broadside?
It's a trade-off. Unfortunately, it can be demonstrated that the bandwidth increases, the gain goes down. So that's. But with the tapering, you can get better.
Yeah, because the conditions of alpha forbid and narrow one.
But yes, that's the point. But as you were saying, when you go up in frequency, the fractional bandwidth it's easier. With 5%, it's much better. And I know I have the proof with a student that you are working with this topic. We can get at least 10%. That's right. And probably even 15, and then it depends. depends about the directivity they ask. For sure, here there is no difference almost between directivity and gain, because up to 100 gigahertz losses are absent, essentially. No? So you just need a good feeder, fully integrated. No? So it's then you can say, okay, I want to reach 40 dB with a small bandwidth, or I want to take 30 dB with 10%. It depends upon the application. We have in mind the space application. Okay, so that's the idea. So it's just a different approach with respect to lens antenna that works pretty well. It's just a different design. Probably they're a little bit flatter, planar. That's the point.
This is an evolution. Do you remember when we started PhD? We collaborated with Makoto Ando and Vito Kurokawa because they are doing slotted wave guides and radial line. And the approximation to the problem.
And we see,
similar.
They still do it.
Yeah.
But they don't use Leaky-Wave theory because no one is prescribing the Leaky-Wave theory. So we keep relaxed.
No, even myself, when I started, I didn't use the Leaky-Wave theory. It's the traveling wave antenna in where you are point by point adjusting how much power you want to radiate and how much it's going to.
Yeah, I remember your antenna. That was the
and there
big
was
one.
a key point in the uniform phase that you are telling us that if you were looking for a broadside direction array, the reflection was in phase and it was impossible to radiate because everything
And
was
you track that
reflecting.
with the asymmetry.
Yeah.
You track that with the asymmetry.
Yeah, this is the point.
That's
This is
the
why you have everything
You
reflected.
practice with the asymmetry, but now what we want to understand with the Cosè, if we keep the overstep and suppress it, we can still taper in the best way. That's the question that we're addressing with Cosè and Miguel in this mix.
Yeah.
So it's
this is nice because it opened possibilities, because I didn't have this in mind thinking about broadside direction with these liquid structures.
The point is that people is saying, okay, cool, nice liquid antenna because there is complex algebra behind, so you need to have a little bit of complex algebra. But in the end, if you have a dispersive antenna, that the beam will change with the frequency. Okay, so if you have a wide band signal, you will get a percentage bandwidth there and the other percentage there. So the signal will be destroyed. You want to have fixed beam antennas. But with broadside, it's another story. And in any case, unfortunately, I think that liquid antenna are used a lot for defense application. Because sometimes you want to just scan.
This is the point.
They want to scan.
No communication.
No communication. It's a matter of killing people. It's not communication.
I think that they use a lot for defense application. You scan when you want to scan.
It's a very simple way to do the scan and not mechanically. Because if you introduce the mechanical, there is another part. And if you do it in frequency scan, you are scanning the same.
Yeah, but see, they have a new life because higher frequency means a small percentage, it's a small fractional band. So you can still do something. Because you can define an instantaneous bandwidth by getting a minus 3 dB. So if the bandwidth is not so large, there is room also in that case. And in any case, this kind of antenna, there's not a waveguide were proposed by Oliner, which is the father of liquid antennas, in the 60s. Then we forget everything because we discovered PCB. Because we want to go up in frequency. Then it's always going around.
Yeah.
Because you change frequency, you change application, you change the technology, and then we will see.
I would say that almost everything has been invented before.
Yeah, but we don't read the paper of 20 years ago, so we rediscover things because we don't go in IEEE to 20 or 30 years before.
Invented by Chinese. So
Yeah.
if you want to look for something new, you think, oh, how good idea I have. No, it's published 60 years ago and implemented by the Chinese. Always.
Yeah, but without going too much into theory sometimes. They don't need it. If you want the results, it's just an approach. In Europe, we are more sensitive to theory sometimes. That's which keep us a sound understanding of the background. Otherwise, artificial intelligence. Will rest. So just let's keep this.
It's what I told to my students all the time. Where are the physics? I want to know what is going inside, and I need to know.
The possibility of modeling a little bit. So using a little bit of a complex algebra to understand what's behind.
No, and especially Italian engineers, they are very
Yeah.
worried about theory.
Yeah, sometimes because we are lazy, because then it's better to use pencil and paper,
Yeah.
and then you go instead of building up a huge anechoic chamber. We are not good.
It's cheaper, the paper is cheaper.
Yeah, and I mean, we are not good in doing this kind of in our university, mainly because our campus are in downtown, most of the time.
They are traders. They convince you to use your anechoic chamber, but they use the paper. They are traders. As Italian, you are selling our olive oil, and you are also.
Yes, that depends. And in any case, I've got a project. I have money to buy a printer, but this is still probably too expensive. So let's see. Let's see. I'm interested in manufacturing because I see that students are interested. That's the problem.
Yeah, and gives a knowledge, a complete knowledge. It's the way why we like to introduce also students in the manufacturing part. Yeah. So thank you very much, Davide, for the presentation. Thank you everyone here for being online and for being here physically. And thank you all the presenters for this nice session today. I think we can close the session. From the line, people, thank you very much and see you. And we will have these videos linked in the webpage of URC Spain later on. We will prepare it.